Well, good morning, everybody. Welcome back to the CIB Presidential Series that we broadcast from Purdue University. As you all know, the theme for this semester's seminars is Distinguished Women Researchers in the Built Environment. And we have had a number of distinguished women researchers come and speak at this seminar. And today, again, we are privileged to have Dr. Kartas. Let me give a brief background about her achievements, and then I'll hand it over to her. So Aslian is director of the BEI lab, and she's also a clinical assistant professor at the University of Illinois in Chicago. She's also a lead AP, is the director of the Built Environment and Infrastructure Laboratory, as I said, and currently serves as the clinical assistant professor at University of Illinois, Chicago. She worked as a postdoc at the University of Michigan, received a PhD from University of Illinois in Urbana-Champaign, and MS from University of Florida. Her areas of expertise include climate change adaptation in buildings and cities, risk and disaster management in the construction sector, sustainable and smart buildings, decision-making mechanisms in construction, and industrial and prefabricated structures. Her research studies are sponsored by DOE, STO, STO Panel of Technology, CPWR, and Centropolis Accelerator. She also has multiple years of industry experience. She received Foremost Leadership Award from the National Association of Women in Construction in 2019. So please welcome Dr. Aslian Kartas.
Thank you so much. Hi, everyone. Thank you so much for the very nice introduction, Dr. Hostak. So today I'm going to talk about the advancements in building technologies, and specifically I want to focus on the climate resilience and adaptation strategies in built environment. So this is my team. Of course, I cannot do that much of it without my team. I have this very smart, motivated students that we work together. And I'm going to talk about the researchers they're mostly leading in my research lab. So we call ourselves Bay Lab, Built Environment and Infrastructure Lab. And before I start my talk, though, I would like to kind of give a little bit of background about my academic journey and how I ended up in this the building technology area. So I'm originally from Turkey, and then was born to this beautiful historical monument structures. It's not that hard to be inspired to be a civil engineer. So I did complete my civil engineering degree in Boğaziçi Bosphorus University in Istanbul. Then I decided to move forward because I was getting interested in green building, ecological building. That's what we were mostly called at that time. And then I found myself at the University of Florida to study on my master's. And then this is a picture, actually real picture that I took. It was, I believe, week 2 or 3. I was in the bus going home from school, and all of a sudden bus stopped, and then we had to wait like 5 minutes for this tiny, cute alligator to complete a trip from one side of the street to another. I was like, oh boy, what am I doing here? But I was so lucky that I was able to get into classes, especially from Dr. Charles Kieber at that time. And I'm being introduced with sustainable construction and also construction ecology and metabolism. So that time, again, the built environment was not that much of a common word. So that's the construction ecology metabolism is the one that's mostly we're kind of using interchangeably. So after that, I moved to University of Illinois, Chicago for my PhD. I believe most of you guys are familiar with this beautiful cornfields here in Purdue as well. And then there I did my PhD mostly on the whole building energy simulation programs. And I did develop some algorithms for parallel computing to make it more efficient and productive, and also develop optimization models for sustainable design and construction decisions, mostly on the computational environment. Then I moved to University of Michigan, and I work also at Oregon University, and had a part-time consultancy job at Walbridge as well. And then that time, I was mostly focusing on occupants dynamics and behavior in built environment. So 2.5 years ago, I finally moved to Chicago, the beautiful city at UIC, and then I was finally be able to found my own research lab, building technology in the science area, built environment and infrastructure lab. So with this journey, starting from the very south of United States and going to north, what I learned is, especially learning fundamentals of construction ecology and metabolism, then working on this computational simulation models, which is widely used, by the way, by engineers, designers, architects, et cetera. I mainly use Energy Plus to develop my algorithms on top of that. But I noticed that even if it's widely used, it has two big gaps. One is it doesn't include the occupants' behavior in it. It assumes that the simulation programs, all the occupants behave in the exact same way, and which is not the real case. And that kind of causes some inaccuracy between what do you usually simulate and then what you get in the real life. And then what I also noticed that in these simulation programs, they're also not taking into consideration the weather changes or how the built technology, how the built envelope system will adapt itself for over the course of the years of aging and also for the future climatic adaptation. So with this in mind, that's what the vision of my current lab. So we do work on investigating climate resiliency adaptation for high performance built environment and always keeping human in the loop. And then these are some of our collaborators. And then this is the main areas that we're working on. And then I want to talk about, basically majorly on the climate change adaptation and then innovative methodologies that we're developing. That will be the main focus of my talk today. So we're particularly focused on building envelope systems. And now let me show you why first. So the 40% of, I think this is a kind of become a common knowledge, 40% of the building related energy consumption is coming from buildings. And then buildings also do responsible for 40% of carbon emission. And among these 40%, 28% is about the building envelope system. So when we say building envelope system, let me go back to here. So we're talking about roof, walls, windows, foundation, whatever you think about the kind of enclose the building itself. But particularly, we're focusing on walls and windows. And then the reason is that we're among that 28% of the electricity consumption, walls and windows, they're more than half of it. And if you include some of the leakages from these ones, so some improvement in these wall and window technology systems will going to help us a lot by finding out, what will be the adaptation strategies for the construction. And as we know that the building stock is getting old and aging in the United States, and they're coming out with some new technologies to kind of improve the overall improvement in insulation, thermal performance, moisture performance of these buildings. So we want to see how these are working and how they're going to look like with the over the course of the year with the climate change in mind. So I'm going to talk about the research studies, but I want to introduce you with our two handsome guys. We have two walking chambers, environmental chambers. This is the one that make from scratch, and with my students, we're very proud of it. It was able to do the test in -40 to 212 Fahrenheit. So this is the one kind of helping us to put the samples, wall samples, window samples in the middle, and then create the weather simulation system based on the ASTM and ASHRAE standards. And then testing sample size that we designed for this one, like 5 by 5, so anything can go in there up to 5 by 5. And then a couple of months ago, we received this more sophisticated one, which is in their walk-in chamber that we do have. And then it has a kind of wider temperature capacity, which we can measure to -40 to 212 Fahrenheit of the weather conditions. And on top of that, we can also simulate wind and rain experiments in this environmental chamber as well. So it has a kind of wider range of the testing sample. So we do have two rooms here. One side is representing the indoor air quality, indoor weather conditions. And then the other side is the one that we are changing the outside weather conditions based on whatever we want to simulate. So the testing sample size is larger for this one, 6 by 6, and thickness can go up to 2 feet. And this is kind of typical how the experiments look like when we do experimental stuff. So we have the two sides. This is the interior kind of presenting the like room temperature, room conditions. And on this side is representing the outside temperatures. And of course, there's a very kind of complicated, sophisticated data collection system in the background that kind of help us to run these simulation models. And this is an example of Windows. Again, it needs a little bit different sensor systems, but the idea is the same, the environmental chamber, and we put the sample in the middle, and I try to expose the sample we're testing to different weather conditions and see how they behave. Okay, so let's start with walls. I'm going to talk about walls and windows. Walls is going to take a little bit more time than windows, but I'm going to give you kind of like, idea of what we are doing, a taste of what we are doing. So with the walls, we start with actually, we kind of approached by a big industrial construction company. I don't know, you're familiar with the industrial construction, offsite construction. Anyone heard about it? Modular, maybe a student, I mean, of course, the professors. Yeah. So I believe that it's going to be the future of construction, especially after COVID. We found out that there's so many advantages of these industrialized offsite construction systems over the traditional, over the traditional ones. And then once we've been approached by this big manufacturers to panel technology, so we got excited because they say that they have some unknown territory that they want us to explore. But let me show you, if, especially the students, if you're not familiar with what I'm talking about, I would like to show you this very short video to kind of showing you how the manufacturing process, transportation process, and also installation process works with these construction, industrial construction wall assemblies.
At WPI Prefab, we believe in helping you succeed. With our manufacturing process, building your finished exterior wall system will be smoother than ever before.
So all the wall, these are 8x10. They've been manufactured in the factory and then being shipped to the
manufacture your finished
site.
exterior wall system in a safe and controlled environment, reducing risk by eliminating exposure to on-site congestion. We build with the highest standards, utilizing the best materials, tools, and technology to build the highest quality product. Our quality control protocol tracks the construction of every wall panel from design all the way to its arrival on the job site. By building off-site, our prefabricated system will save you time on your project schedule, with faster building dry-in and an earlier start to your interior construction. With a diverse portfolio of different exterior claddings and finish options, our finished prefabricated exterior wall panels can meet the design needs of a variety of projects. Our system brings value to the project. By including the exterior finishes on our panels, we can increase efficiency by building with less manpower and reducing equipment costs associated with completing the exterior envelope of your project. To learn more about what WPI Prefab can.
Okay, so I hope if you're not familiar with the process, this kind of gives you a better idea about, what we are basically working on. And these are some of the examples, like the one that you watch in the video. This is, it was this, the panel. So there are like 13 layers on it, and it comes with like water barrier, vapor barrier, insulation, everything like packed together, and then ship it to the site. This is another rain screen system, they call it. So again, it's a very similar process with, again, the usage is variety of like hospitals, high-rise buildings, warehouses, you can name it, residential buildings. So that's the thing that we started working on. And then we get the question of, hopefully I can, sorry. Move on to the next slide. Oh, there we go. Okay. So the question we got from the manufacturer is that, so they were in the industry, they're mostly find out the thermal performance of this kind of wall assemblies, window assemblies, using a software called Therm. So it's a widely used software for the designers, engineers, architects, and they measure it based on the given drawings, technical drawings and specs. They do kind of find out what the thermal performance is, and mostly thermal performance is measured by R value, thermal resistancy. So the higher R value meaning that your wall is performing better. But they were saying that, okay, this is a widely used version, but we believe in that the software is not actually reflecting what the actual thermal performance of our wall panels are. Because they believe in that this is mostly done for the traditional assemblies like precast concretes, et cetera, but not actually, or maybe need some calibrations for the prefab wall panels. So with this in mind, we decided that we're gonna test these. I call this like a surgery. So we receive these wall panels and then we open up, we replace our sensors in it, heat fluxes, thermocouples, et cetera. And then we measure them, their thermal performances in our environmental chamber. So this is how the inside looks like. This is the two rooms I was talking about. This part is representing the exterior weather conditions, and this part is representing the indoor. And then your wall is basically coming like a regular building, come in the middle, and then you start measuring the thermal performance if that's what you're asked to measure. And then there's the simulation part. Okay, so I'm just gonna skip a little bit more on the methodology part and get into the results. So what we found out that based on our experiments and based on ASTM standards, we found out that we test them in the 65 Celsius to minus or 150 Fahrenheit to 3 Fahrenheit. So that was the boundaries that we kind of select for Chicago area, the average lowest versus the average highest, including the solar radiation. And then we did the same thing on the computational environment. And then what we found out is that there's a 17% differences between the experimental versus the computational part. And then that 17% R value discrepancy, again, it's not something that you can ignore because there's so many different implementations of it. So first of all, if you underestimate the thermal performance of your wall systems, that means that you want to go with a higher HVAC system, with a larger capacity of HVAC system. And then that kind of brings along extra utility bills, extra initial costs, and also, maintenance, et cetera, will be kind of more costly than having something more ideally smaller based on the overall performance of your the walls. So we specifically work on the hospitals for this particular case study analysis because the wall that we analyzed was majorly used for the hospitals. So we did put this one in a typical reference building in the Energy Plus, and then we found out that we try with the experimental R value and then computational R value, and then see over the course of the 20 years, the life cycle time, or the life cycle time will be like 50 years or so, but from the owner's perspective, 15, 20 years make more sense most of the time. So we found out that if you underestimate the R value of your wall system for the typical hospital buildings, so you're basically missing $400,000 from the utility bills. And that will be the equivalency of annually taking 22 cars off the road or 19 household electricity consumption. So with this mind, like that 17% again discrepancy, if you underestimate the R value or the thermal performance of your building, again, it may cost you more money from the owner's perspective. And after we completed this one, we ask another question. Okay, so this is again, we're still working on that project, by the way. We're trying to understand what causes that discrepancy specifically, and then what needs to be improved or calibrated in the simulation, computational simulation environment, so it will be matched with the experimental results for the industrial construction prefab wall panels. We also ask another question about the heat waves, the resiliency of these walls. The specifically for heat waves that we focus on, the first of all, I think this is very important information. The heat waves in the United States killed more people during a typical year than all other natural disasters combined. I think this number is very important, and the walls and windows, again, they play a major factor when you're sitting in your house or building and exposed to a heat wave. And then what we are seeing is that this increasing trend, the average number of heat waves occurring every year. The average length of individual heat waves, how the length of like 3 days, 5 days, 60 days, average length of annual heat wave seasons, how it's increasing, and also the intensity. Again, there's a slight change here. So we particularly focus on this one to understand the resilience of these wall panels. If we see that these are going to be the future of construction, so how they're going to adapt to these, these including heat wave events. So to kind of measure that one, we focus on 2 variables. So it's kind of different than the R value, because when you have this, when you have this, the heat wave phenomena, so you need to kind of understand how that the wave is kind of going through into your building. So this is your wall, and this is the outside temperature, and then the wave is coming like in the big sinusoidal waves. And then you want that your wall kind of minimize it and then have it, as less as possible, have it penetrate through the inside condition. So with this one, we have 2 variables. We did measure the time lag, and then we also did measure the decrement factor. So time lag is basically the difference between these 2 peak times and your sinusoidal waves, indoor and outside condition. And decrement factor is the ability of the attenuation of your sinusoidal waves compared to inside and outside. So you want your decrement factor as low as possible. You want this as minimal as possible. And then you want the time lag as long as possible. So that's or as big as possible. So that's what we were looking for with these prefab wall panels. We did 2 simulations in this one. The first one was the Chicago heat wave, which occurred in 2012. And then the other one was Phoenix, which happened actually last summer. It lasted pretty long. And then this one, it was a 4-day simulation. And you can see here that, the average of 4-day, the fluctuation of the temperature, and then how the actual one is the blue one, and then the simulated one that was in our environmental chamber, how they're very well matching. So that means that, we were able to accurately simulate those conditions and then see how this the prefab wall panel actually adapted itself to that condition, heat wave condition. And actually, as I mentioned, that the decrement factor, you want it as low as possible, and then the time lag, you want it kind of high as possible. So you want your product somewhere here. And these are the ones that we collected from the literature. Again, there were so many studies made on this, but not on the specifically for the prefab wall panels. So that's what we were looking for. And then we found out that actually it's, it's doing pretty well compared to the traditional conventional wall system. So this is the one of the studies that we did. We still have, a couple of other wall panels that we are working on and see how they adapt themselves with these heat wave conditions. So this was Chicago was one of the heat waves. It was kind of shorter, 4-day heat wave. The other one happened last summer. I think most of you heard about it in Texas, Arizona area. And that was a pretty devastating one. The Phoenix hit 110 Fahrenheit, which is 33.3 Celsius in 54 days. So the intensity and the length of it was pretty long, and unfortunately causes more than 600 death tolls in 2023. So we want to see how this one works. But for this time, instead of only simulating the outdoor temperature, we also want to add the solar radiation, because you can see the total difference here with or without solar radiation. The orange one is the solar radiation, which makes it as peak as 71 Celsius during the day. Okay, so your temperature can be around outside temperature 40, 43 Celsius, but with including the solar radiation, it peaks up pretty high. So we did simulate this one for 2 weeks in our environmental chamber. And again, you can see here how the outside temperatures and actual outside in our experimentals are very well matching. And then this is an ongoing study. So we will measure 2 more samples like this. And then we try to understand, okay, so this much heat is being basically stored or being rejected or exposed to the wall itself. And what can we do about that, right? Can we utilize from that energy that's the walls that are being exposed to? Can we redirect them to something else in the house? Can we charge our phones with that energy? Can we store it to heat the water maybe? So this is why this experiment specifically is going to be focusing on the heat storage system of the walls itself, and see how we can utilize, how the heat storage capacity of the walls and how we can utilize it from that for the future applications. Okay, so this was the hot weather conditions, and then we also flipped the coin. And then we want to see how these wall panels are working on the cold weather climate, because that's another other end of the boundaries. But for this one specifically, cold weather, the phenomena is, I talk about like decrement factor, time lag for the heat wave. For the cold weather condition, the problem is mostly the moisture. Because when you have the moist kind of penetrate through your walls during the summertime or during the rainy season, and then when it gets frosted, then you will have the water trapped inside of your house, inside of your building, inside of your wall, and then starts accumulating and creating moisture or mold issues for your building. And a mold, again, it's really bad for the occupants' indoor air quality. It directly affects their health. And then it also damages the structural integrity of the building itself over the course of the years. And also, it really perishes the insulation, and then will have negative impact on the energy consumption of your building, because the less, worse insulation on your walls, meaning that you're going to use more energy by the end of it. So these are some of the pictures, damage pictures of how they're affecting. Again, the main idea is we don't want them to trap inside of your wall systems. And then this is, again, some of the frost damage examples, how they've been kind of affecting your building and what happens if you let it go through over the course of the years. And again, this is especially bad phenomena with the cold weather conditions, because it got frosted and then there's no way that the water was going to let go the outside, and then it starts accumulating moisture and then mold by the end of it. So for this one, we did work on one of the advanced building materials, vacuum insulated panels, VIPs. Has anyone heard about VIPs before? Yeah, vacuum insulated panels. Actually, they've been widely used for insulation purposes, like for your cooler, for the refrigerant systems. But then late in the last 10 years, they started, looking for applications specifically for the buildings. So the idea here is, this is a typical, this kind of thin layer. I don't know if you can see here, but as I mentioned that for the R value, typical R value, you kind of call it that thicker, higher R value is better. So as you make your insulation thicker, then insulation, the R value gets higher. The vacuum insulated panels, though, they try to do the opposite. They kind of vacuum it up and make it like very thin layers of insulation panels. They're very fragile, though. So, and then they try to kind of get rid of all the air that can able to, be on your insulation, and then kind of superior or double the R value of your thermal performance of the VIPs. So this is a kind of typical application example, how it can be applied to an existing building. This is your VIP here, and then they added like other water water vapor barriers on top of it onto your brick system, or it can come like similar to our prefab wall panels that I showed you, kind of come in like in a package, and then we'll deliver it to the site. So what we did here, we kind of worked together with NREL and Alaska, and then also the Cold Climate Housing Research Center. They did developed their own a VIP panel. And then they also put it on a nice kind of prototype housing unit. So they claim that the R values of this wall is 76, which is phenomenal. Like, for example, if you have an R value of 15, 20, that means, you know, if you have a kind of okay, good insulation. If it's 30, even higher, that means it's pretty good. So having R76 is really, really good for Alaska region. But the question we ask, okay, so R value is pretty high, which is amazing, but still would they work in this extreme cold weather conditions? Because they still get rain and then froze tiles, etc. And then for that one, we decided to work on the water content and moisture issues this high insulated panels may create. So we did do a simulation on WUFI. It's a kind of moisture simulation model. We have the weather file we insulated. So we install it to our software system, and then this is this wall here. Okay, they have the metal panels outside of it, and then you do kind of simulate it layer by layer in this simulation program. So from outside to inside, you will see what's going to happen as the water travels through your wall. And this is the result we got. This is the time isoflat graph. So that's a very typical, you know, moisture water content graph that you want to see. And then for the first and second layers, from outer all the way to your VIP panel, we don't see that much of a problem with the moisture. So we want to focus on, okay, what's going to happen starting from, you know, it penetrates through the VIP panel and then go through additional insulation and then go through the indoor interior side of the wall. So these are our temperature to relative humidity, and then this is the moisture accumulation. So you want your moisture is going to stay below this benchmark line. So for this example, we're good at number 3 and number 5, which is the interior side, and then right after the cold weather goes through your VIP panel. But the problem starts from the layer between the VIP and the interior drywall or the metal sheet plywood that you have. So you don't want them to go above this part. If they do, that means that you may have a potential moisture problems with your assembly, with your design. And then we also have this nice 5-year prediction based on these analysis. And then we do have the top one is showing how the temperature is going to change. And then this one, how the water content is going to accumulate over the course of the 5 years. So let me show you very quickly how they're changing. So what we are seeing here, again, the water content, it goes through the VIP, and then still we're seeing the accumulation in between. And that's the part that we are creating the problem, the accumulation of moisture over the course of 5 years. And that's going to create, again, if it stays there longer than that, may going to affect your occupants' health, the structural integrity of your house, and it's going to damage or perish your insulation, and it will affect your overall energy consumption, thermal performance of your building. So this kind of go through 5-year accumulation again. And then we kind of, what we found out after this, I'm just going to stop it here. Oops. Okay. So we have this traffic light system kind of showing, you know, what will be the risk of mold growth. So for the top, the outer layer, we don't see any mold growth issues. But the inside, this is the inside of this tiny house, we do see a medium risk of mold growth, meaning that there's a possibility of the frost problems on your insulation, on your traditional insulation, kind of attached with your VIP wall, VIP panels, and then that's going to have the mold growth and deficiency in your R value. So they need to look for more, you know, better alternatives to kind of have that the water or the air kind of travels through outside, because you have a very nice high R value, but apparently it causes the water trap inside of your wall panel, and you don't want that. And then we'd also make some recommendations. Again, R value is a great measurement, great metric. Everyone is very proud of it. Higher R value, better thermal performance, but it should not be the sole measurement, sole metric for your buildings. The moisture content, water content should be also analyzed to before your product that's going to be available in the market. So that was the the recommendation of this, the wall panels, VIP vacuum insulated panels, departure to before they become the available in the market. Okay. So I completed the walls part. Again, I mentioned that we're doing a lot. I just want to talk about a few of them because of the limited time we do have. And also I want to talk about the other part of building envelope systems that we do work on. So it's the windows that we are working on. And then I'm going to talk about two projects today. This one, we're working with Oak Ridge and DOE together. And then we try to understand the air leakage, the impact of windows on the air leakage of your houses. Why it's important? Because it's the air infiltration through building envelopes is responsible for 30% of your energy in a typical residential building. But the thing is, though, we don't know what happens when you replace your windows. What will be the impact? Which was kind of interesting to me when we start talking with Oak Ridge. We're going to do this study because I thought that supposed to be well studied before we go with more advanced complicated versions of window installation systems, etc. And if you have this uncontrolled air filtration, air leakage through your house, and that will first of all is going to have problems with the moisture accumulated in your building. You're going to have cold drafts, which I do see a lot right across the street. That with the restaurant we went last night, I think the houses are getting pretty old on that street, and they started covering with this plastic sheets, etc., to kind of prevent this. But unfortunately, I think they're going to have more moisture issues even if they try to keep the cold draft away from them. And then unwanted noise, the lower indoor air quality, of course, the dust, VOC, airborne pollutants. So it's had a huge impact, the windows. And then since the impact of window replacement on the air leakage is not known, the weatherization programs specifically targeting to low-income, overburdened communities, they do exclude the window replacement. They don't include it because they say that we don't know the impact and it's too expensive. We don't actually know it's going to make any changes once we replace the windows of these houses. So with this in mind, we did, this is a field study we start with. We did analyze 10 houses up to this point. And then the results that we get before and after replacement, it was actually kind of diverse. So some of them kind of showing great improvement when the windows are replaced. Some of them didn't show that much, and some of them outliers, like 40% or something. This is one of them. Like our team was very surprised by the result, like pleasantly surprised. So then we talked to DOE and Oak Ridge, and then we're on the way of getting additional grant because we said we need to analyze more houses in the field. And then we also want to test them, some of them in our lab, in our environmental chamber, in a more controlled environment, and see what kind of variables actually impacting these, diverse, the air leakage improvement for the windows specifically. So this was the air filtration one. And then we also work on innovative methodologies. My very nice colleague, Dr. Özevin, she's the director of non-destructive evaluation lab at UIC. So we're working together with a lot of projects. This is just one of them. And in this one particularly, we're focusing on the argon gas in the window. So when you have, when you have IGUs or the window systems, they mostly filled with argon or krypton. Krypton is less common, but argon to increase their thermal performances. And when you have them filled with, instead of air, with argon, you're going to increase, this coming here, 7% improvement in the overall performance of it. But we don't know yet at this point that the manufacturers claim that when you want to have the argon-filled windows, they say that this should have at least 90% of argon in it. But we still don't know when they arrive to the site, they actually have that much argon in it, or what happens, or how do they degrade over the course of the years, which will have, again, or leak over the course of the years, which will have impact on your energy consumption of your building. So there's one analyzer available in the market, the existing methodology, they call it to measure this argon gas content, which is around $40,000 to $50,000. And it's very hard to get it. It's not accessible. It's not affordable. And because of that, not many people, they don't know about the quality of the windows they do receive. So with this in mind, we want to develop this non-destructive methodology, hopefully competing with this existing one, with low cost, accessible, and portable, to be able to go and check this the argon gas content in those window systems. And we're working on this one right now. I think you see our the new experiment setup. So we're collecting data, and then hopefully, the results right now, the preliminary results showing that we're on the right track. But again, it needs a little bit, 6 to 8 months kind of work on it to be able to that we can confidently say that, we did develop this one. We'll be hopefully competing with the existing methodology in the market. Okay, so now we're kind of tying back to where I started. So my academic journey, as I mentioned, that will right now with going with the Built Environment and Infrastructure Lab. And then with all these years of my training, my education, my experience, again, I'm trying to kind of find a way to how I can integrate these ones in a simulation environment with experimental results, field results, the computational results we do have. How can we integrate it with the mind that the climate change, weather predictions in mind into these simulation programs? So one of my students just started working on this, the weather scenarios. They're different, based on different carbon emission strategies. There are different kinds of the weather predictions, like you can see here, and you can, maybe you cannot see here, but like every year, 2020, 40, 60, 80, how we are thinking that each year's overall medium temperatures are going to increase over the course of the years. So all these things that we're working on, my ultimate aim is integrated with this evolving climate conditions, and then see how we can improve this existing computational simulation programs to have a better, more accurate estimations, and hopefully get a better, building codes, energy codes for the world, for the building technology and science environment that we're in. Okay, so that's all for today. I want to say thank you on behalf of my students. I hope you enjoyed the presentation. Hopefully I didn't take that much of time. Okay, it looks like I was a bit worried that I may be talking to, but it looks like
no, thank you very much. Let's give it a big round. Let's open the floor for questions. Go ahead, please.
So you seem to be addressing.
Your microphone, you can't think of it.
Oh.
I had good news on you. So you seem to be aware of the air leakage problem associated with windows, but I was wondering if you've looked at the air leakage problem associated with the system of panels that you put together, and how you can study that, or how that affects the overall performance of the whole building system with the high quality insulating panels.
That's a very good question. Actually, that's the second funding that we've received for stove panel technology that we're going to start working on, I believe, as early as April. So we're going to look at, because those wall panels, when they kind of put together, there's a kind of joint system, kind of glue system between them. And then we are going to look at how the air leakage works with different kinds of these, the joint materials, and how the water also penetrates through that as well. So yeah, that's going to be our upcoming project. Hopefully, again, beginning of April or beginning of summer, we're going to explore that one. Thank you so much.
Great, thank you for that question. Yes. Yeah, try speaking through there. Let's see.
So in this slide 3.5, you talk about like cladding and prefab wall panel system. So you talk about saving time and increasing the efficiency. So what about the cost factor? So, so is there any increase in cost as compared to the traditional wall panel?
Which increase in cost? Sorry, I think I didn't. Would you mind repeating? Mhm. Yes. Oh, that's a very good question. So when, like, you mean like initial cost, like how much you need to pay? So we did some analysis on that one, which includes the transportation cost, you know, the time that your crew needs to make the trips to the site itself. And then when you include all these, starting from the initial cost, manufacturing stage, transportation, all the way to the site and installation, when you include all of them, actually, there's not many differences between them. And then the risk that you're covering is way more than, with the traditional one, because weather is not a big impact for you anymore. The congestion is on the site is not a big problem for you anymore. So you have basically more control over it. Of course, there's some little bit of, as far as I know, based on the type of wall that you select, right? Because there are a lot of varieties. There might be some, initial traditional versus the prefab. There might be some initial cost differences. But when you make the trade-off, the risk versus cost, it kind of pays off itself. That's a very good question. Yeah, go ahead, please. Well, they're building codes, right? And then all these panels are based on the building codes. So there's not, if you're asking like electric vehicles, there are incentives, right? They're giving it to people buy electric cars, that's you're getting incentives. If you're asking if there's something similar for the prefab, wall panels, as far as I know, there's nothing like that. It's just the owner's decision which one they want to go with. Sure.
Yes, go ahead. We'll take one here and then go.
Is it fair to say, based on your research and other research going on, that what's currently the standard using an R value is probably going to become obsolete if we go down the road 4 or 5 or 10 years because of better ways to measure?
Well, I think what I meant to say is that R value should be the metric, but it should not be the only sole metric that when you're selling your product or how you want to see the impact over the course of the years. I think hydrothermal performance, which includes moisture or mold growth and thermal performance together, should be done together for the products, especially for the advanced building materials, advanced building technologies or systems. It should be, done together, not only focusing on thermal performance, but also the moisture content. Yeah.
There was a question in the back.
So are the sizes customizable, like as per our project needs?
For the experiment,
Yeah.
you mean? Yes, because there's a kind of limited size that we have. So they kind of make it for a 6x6 for us if they want us to use those wall panels or window panels in our environmental chamber system. But we do that's a kind of process that you have to be very diligent about, because we usually go to, for those, if they're gonna make a wall assembly for us for the experiment, we wanna make it as natural as possible. And then we go there during the assembly time, the shop, and then we randomly select, which material is gonna go there or which insulation is gonna go there. Because they come like a package, and you don't know if they try to make it as the best they can. So we want to prevent those kind of little bit tricks they may play with, and then we go there during the assembly time in the shop, and then we randomize the total process, and then they kind of customize it based on the 6x6 or 5x5 sizes that we request.
Yes, go ahead, please.
So I really enjoyed your presentation.
Thank you.
So what are some of the challenges that you had when you were doing your experiments? I mean, did you have to model, make changes in the models or in the actual setup of the
Um,
experimental setup?
I think the one that we're going through, actually today I woke up to that message, the environmental chamber, I think the electric panel just broken, so we had to shut that down. So we have that kind of issues. But I think if we go back to your question, the challenge is to try to understand layer by layer how the thermal or the conductivity changes, because that tells a lot. And these prefab wall panels, as you see that they're just coming together. So we try to be there during as I mentioned that during the assembly time, and then put our sensors as assembling it. If not, opening it and try to find out where will be the weakest spot so we can measure it. And we have to be as independent as possible, right? We cannot just favor on these prefab wall panels over tradition. We just need to report whatever we're seeing. The challenge, I would say, I think the 2D versus 3D simulations, especially. So I mentioned the therm here. There's also the 3D thermal performance analysis that you can make. It's called like mostly, I think they call it a console and the software. So with the one that, the 2D just goes through like linearly and then see how the thermal performance. But when it comes to the third dimension, so it's kind of adding a little bit complexity to the overall system. But again, try to kind of find a way what is causing the inaccuracy between the experimental and computational right now. So we're looking for the answer to that question. Where our hypothesis is that most likely they're kind of like put together in a high quality, or more controlled environment. So the quality of work is better than what you can work on, vertically on the construction site versus, these are horizontal. So that might be the thing. But again, we're still looking for this, doing the sensitivity analysis. I think that's the most challenging part for us to find out which variable may cause that inaccuracy.
Thank you so much for your presentation, and I really enjoyed it. So during the presentation, you talk about like your approach always including the human in the loop, and probably due to the time limit, you mainly talk about the experimental like a reserve. But what are the higher level like some pattern research activity that you can better perform the occupant dynamic or like occupant dynamic to perform the more precise the building energy simulation?
That's a very good question. Yeah, we do have two main or two different things going on with them. One of them is doing the data analysis and the building level, city level, nation level, how people's energy consumption behavior and patterns are changing. And mostly we're looking for how the socio-demographic level impacts that changes. And then the other one that we're working on, which is more related with the moisture issues, right now we're in the process of, setting up the houses in a kind of overburdened neighborhood in Chicago. So we want to go see the houses and then measure their indoor air quality, and then also talk to them and see, the moisture issues they do have in their walls versus what they're experiencing, how we can, if they're matching, they're showing any similarities. Because especially for the moisture, when it becomes visible, it's kind of too late to remediate it. So because it's already impacting a lot by occupants, the structural integrity. So the question is, can we catch it when it's the hidden mold behind the wall? Because when it's hidden, no one wants to take any responsibilities about that. So we've been working on with these neighborhoods, closely. But the problem is that, okay, listen, you're going to come to our neighborhood, you're going to visit houses, and you found out that there's mold in their wall. So what you're going to do with that, right? So it's creating a lot of liability issues. So we try to kind of develop this trust relationship. It takes time, and then try to understand, also inform the occupants and also house owners, landlords, how we can remediate it and how that's impacting their overall well-being, basically, and also the structural integrity of the houses. So that's a good question. That's an ongoing project. Actually, we kind of have 5 houses in the list, so we will hopefully visit them in 1 month or so, and then I will have more data, I would say, to talk about it, I guess. afterwards.
Yes, go ahead, please. Can you use that? Just press that button.
Thank you very much for the presentation. It was amazing, even though I got towards the end. So my question is, because contractors are going to be the one kind of constructing this on sites, what are going to be like some construction metrics that they should look out for when they are constructing and putting into place, knowing fully well that there are possible failures probably due to transportation to the site, just probably during construction itself, during construction in the factory itself, and then probably sometimes during construction on site itself, that like 3 different modes of failures that they could have. So what are some metrics they could check probably prior to installation or after it's been installed to be sure that this prefab elements are actually in the right way and the right states upon construction?
Oh, so you're asking like the after installation inspections and stuff, who is doing that? Okay, that's a very good question. As far as I know, even if for the traditional or the prefab in terms of thermal performance, I don't think they do go and check what happens after they've been installed. That was actually kind of interesting conversation we did have with one of these big companies. They're working the computational simulation firm a lot for the industry companies. They only look it up, what's the initial, what does the design looks like? And then they decide, okay, this is how the thermal performance should work. And then they call it good. But when we ask them, okay, do you make any after visits? Are they been, installed properly? Or are they been, working in a way that you're foreseeing in your computation simulation? Unfortunately, the answer was no. So that kind of also triggers that, that no would trigger us as well to kind of dig in more the experimental computational simulation, and then hopefully we're going to extend it to the field experiments as well and see how those things are working. Not only the right after installation, but also like after a year of usage, right? So the degradation, how it's happening. So we're also trying to understand that part. And then the aging process, I didn't talk about it today because of the time, but that's also, we're also looking up like how those the wall panels are aging, or traditional or prefab wall panels over the course of the years when they exposed to weather. And then how can we kind of develop this quality metrics, quality measurement metrics accordingly? So yeah, that's a very good question. Thank you.
Yes, Chelsea, please.
So I think your comment raised an interesting point. Yeah, is it possible, or have you thought about instrumenting some of the buildings in which these panels have been placed so that you can do maybe a 5-year or 10-year assessment of the degradation and the impact of the degradation on the performance measures?
Yes, and that's a very good question. Actually, maybe I can show you my slides here. Sorry. Let me see if I do have that. Oh, yeah, this one. Okay. Can you see my slide? Okay. So this is one of the aging experiment that we're working on. It's not the field yet because that's the that's what I want to do, like similar to what you have the tiny house over there, or maybe a trailer, have it and just continuously monitor it and see how things are changing. So we do have a little bit space issues on my campus. So we start with a smaller scale. We did develop these mini walls, and then these are kind of traditional walls with a continuous installation on them. So continuous installation is also becoming a kind of, it's not mandated for the all states yet, but it's becoming an adaptation to kind of adding this pure installation without any breaks in it, any stop breaks. So then you will improve the overall installation performance. So what we did is we kind of developed these little tiny walls, and then we put them in our environmental chamber. And then we'll run this ASTM experiment, thermal conditions experiments. And then the next step, we're going to send it to Oak Ridge. They do have this weatherometers, which kind of simulates for 6 weeks of exposure to solar radiation, wind, etc., and then kind of age your product. And the reason the walls are mini because of the size of the chamber. And then they're gonna send it back to us, and then we're gonna measure their thermal performances one more time. What happens, you know, after that, the aging. So again, because of that's my ultimate goal, having a nice, you know, continuous data collection facility, maybe changing the different walls or, you know, insulation systems. Those are been done with some of the big labs, and then see how their effects and how, you know, the degradation is happening real time within a traditional house. But right now, you know, we're working on this scale. Hopefully, it's going to give us an idea, though. That's the first step to going through agent performance.
Yes, go ahead, please. Please press that button so we can get on here.
So thank you for the presentation. I want to ask, why do you really focus on prefabricated material? I believe you know, prefab has not been it's not scalable in all other countries aside. I think it's very much in you know, Europe, some part of the US. I believe there are some other material that perform better than, you know, traditional method of construction and all, and you know, that is also affordable. You know, there are quite a number of research on prefab that have modular construction so far that you know, I was opportunity to be part of a research, and the cost of modular construction in places like Africa, it's not affordable. In fact, some part of Africa does not have anything, you know, that has to do with modular or maybe prefab material. So I'm thinking maybe you might be looking into other material that can be scalable even to other part of, you know, Africa and, you know, other country that doesn't have, that is not as rich as the US. Yeah.
Thank you so much for your question. And I'm glad you refer to Africa, because the reason that I say this will be the feature of construction, it's already widely used in the US, but not, as you mentioned, that, you know, some of the countries or continents yet. But good news is that the big manufacturer that we work, they're going to open up a big factory in Africa very soon. So they're working on it. So that being said, these are going to be affordable materials and accessible materials, not only for, you know, developed countries, but also, you know, the others, the developing countries as well. So with this in mind, I slightly disagree with you. You know, they're not for the rest of the world. They're coming like that. And then again, it's new. Like when you develop something, the computer prices, for example, when they come up, they were so high, right? As they're going lower, or same with the electric vehicles. So the technology is always higher when they first implemented, but as the usage is getting increased, when they're finding more productive, efficient ways of manufacturing, what the technology is evolving, so it's going to become more affordable and accessible.
Thank you for those questions. Let me go over to the audience online.
Okay, let me.
Do you have any questions? Please open your mic and ask. Anybody online? Any questions? Okay, I don't hear anything. Any further questions from the audience here? Well, let me ask my last question then.
Sure.
So you mentioned earlier about Chicago, and you also mentioned that you know, walls, roofs, windows are the biggest culprit for energy wastage. And given that Chicago has number of old buildings,
Yes.
is there anything being done to reduce energy consumption?
You mean by the
By window
federal
replacement or
So I
retrofitting?
think those the continuous insulation systems, they're becoming practical, and then or the suggested versions for the existing buildings to increase their insulation. So they kind of come in like big sheets, and then without disrupting the occupants in the old buildings, you kind of put it from the outside to kind of increase the insulation, and it will provide, you know, given another 10 to 20 years for the better thermal performance of those houses. So the pace of that continuous installation adoption, it changes from state to state. But Chicago, we're not there yet, surprisingly. But for example, in Michigan, when we talk to the contractors, they're more aware of that continuous installation systems because they already adopted in their codes. But in Illinois, we're not there yet, unfortunately. So, but you're right. Like there's a pretty old building stock, and there's so many issues going on with them. Like for example, the window test we did. One of the houses were in the very south side of Chicago, and they were getting some funding from the weatherization program, and then that was one of the unique houses they were able to get window replacement funding. And then we did run our window leakage testing before and after the window replacement, and then the house was extremely leaky. So the window couldn't even, the pressure inside couldn't even reach the one that you typically needs to reach. So the house, there's so many issues, unfortunately. It's, one thing, changing one thing is not enough for improve the overall house. And that was, again, with the window replacement was the very last thing, were multiple grants that the single family house received, but still it wasn't enough to make it in a way that should be a kind of, have the well-being of the occupants, perspective, unfortunately, wasn't there yet.
Thank you very much. Any pressing questions before we close the session? Well, let's give it a big round of applause. I think that was fantastic. Thank you very much. And thanks to all those who are online for attending. Thank you very much. Appreciate it. We'll have another similar session coming up pretty soon. Every week, as you know, we have another speaker. So please stay tuned. Thank you all.